Hello everyone. This lecture is lecture 26, following up series of our unit 3 actually. We are now starting to ray optics. Ray model of light. We'll understand overall here how ray model of light works. We'll talk a little bit about what light is here, and then later on in unit 4 we'll talk more about light. Our life is encompassed by light, so we want to know how it works better. Understand how reflection works with this ray model and how images forms. That's the learning goals for this lecture. Light is actually electromagnetic waves. We watched a short video on that, and that's how much we need to know at this point. We have electric field oscillating, changing direction and magnitude all the time, and we have magnetic field perpendicular to that electric field, and they oscillate together. That's what light is at classical level. Let me not say too much here and confuse you. And this is called an electromagnetic wave. So this is magnetic field here, this is electric field, and this is their directions changing. They're perpendicular to each other. We won't go into details any more than saying light is an electromagnetic wave. It behaves like a wave at a macroscopic level. We can't really see that it's a wave at macroscopic level. How we see it is beams of light, right? We can always observe that, and that's the ray model of light. We assume the light comes in straight lines and hits stuff, reflects and passes through sometimes. That's the ray model of light, and we're going to represent. There are actually a beam, and there are many rays, billions of rays in the beam, but we'll represent them, choose one or two rays, draw the lines to understand how light will behave under certain circumstances. And this will involve refraction. Later on in this lecture we'll talk about reflection. General knowledge is that light has a speed. Speed of light is 3 times 10 to 8 meters per second. That's 300 millions. 300 times 10 to 6. So 300 million meters per second. That's the speed of light in vacuum, empty space. If the light goes into another medium, it changes its speeds, and this equation gives us how its speed changes. And that's all actually we need to know about it. Not much tricks and so on. Speed in a medium with an index of refraction n is equal to this. We'll get back to this later. These are all ray optics of ray model of light and related to ray model of light. Now we want to talk about how we see with this ray model of light. What happens is that any object, opaque object, reflects light in many directions. I have a tree here. Light comes to hits any microscopic part of it and reflects in many directions, like in this figure here. And some of those comes to our eyes, collected by our eyes, and we see the images. Our eye actually has a lens. This is a convergent lens. We'll get to that as well. And that lens focuses the light that comes to our eye. Depending on how much light we're collecting, we're seeing a bright image or less dim image, which is why if it's a little bit dark, there's less light, so we are seeing images as dim. So that's how the ray model of light works. Many light rays comes to many directions, and this is how we see. Some of them comes to our eyes and collected by our eye lenses. There are devices we use like laser pointers that are pretty much representing ray model of light. This is a collimated collected light that is directed in one direction. It's a very intense light, which is why it is dangerous to look directly at. There are some others like flashlights where light is again collimated, not as intense as a laser pointer, but it has also one direction light. There are also large sources of light where light goes in any directions, and we again see whatever comes to our eyes. To be able to see an object, the light rays from those objects should hit to a screen or comes into our eyes, as we said. This question I include here because it represents a pinhole camera. Initial building of cameras had this idea here. If we have a small opening here and we have a light source, how do we see the image of that light source in the screen? To be able to see that, we'll send two light rays, one from the top. It will go from the bottom of the hole, from the hole, hit the screen. I will send another one. There are very few light rays are passing here because it's a very small hole. And as it turns out, the top, let's call this one, and bottom two light rays, if you follow up, the bottom one hits here and the top one hits there. So what we're gonna see on the screen will be an inverse image. That's the idea we get from there. So the answer is B here. What is the image on the screen? This page I'm going to be skipping. It's a very similar idea to what we talked about. How we see is some light rays comes to our eyes, our lenses collect them, makes an image at the back of our eyes, and our nerve sends a signal to our brain that there is an image, and our brains tells us what we're seeing. As we've seen in here, probably you will cover this in another bio course or so. I don't really want to talk about it too much, but as we see here, the image will be inversed, and our brain knows that image will be inversed and tells us that it's an upright side of image, which is amazing how eye works. Please read more about that. Again, there are light rays come in, reflect in many directions, and some of them comes to our eyes, and we see those objects. The color we see is the color reflected. Each object reflects a certain color or mixture of colors. That's how we see different colors. This is the full spectrum of light here, and this part is the only part we can see. All the rest is invisible, but there's still light, there's still electromagnetic waves, there's still electric field and magnetic field oscillating perpendicular to each other, and which is why we call this electromagnetic spectrum. So if we are seeing an object that is white, it reflects or transmits. Sometimes we have transparent objects, passes that line and we see them in that color. All the spectrum, visible spectrum, so all is equal to white. If an object is reflecting only red, we see it as red. If it's reflecting only blue, we see it as blue. If it's reflecting red and blue, we see it as magenta. Or again, transmitted. If it's reflecting blue and green, we see it as a cyan or aqua color. This color here would be a good example of that. So it's all about what color they are reflecting and transmitting. If they are not reflecting or transmitting any light, then we see it in black. They absorb all the light that comes in. which is why we see the sky blue as the sunlight comes in. Sun is mostly yellow, yellowish white we can say. Yellow reddish part is passing through the molecule in the atmosphere, as you see in this picture, and most of the blue light is scatters. And as the blue light scatters, we see the sky blue as we look up. If we are standing, however, somewhere the sun is setting, the most of the blue light is already scattered over here, and we see the passing reddish orangish parts, so we mainly see the sun in that spectrum range. Another example, white clouds are reflecting all the visible spectrum, that's why we see them white. And this image is here showing the what we call black body spectrum of sun. It emits light at all these spectrum. This black curve you see here, this is the sun's overall, well, actually the full figure is the sun's overall emission, light emission. And as you can see, we have purple, blue, green, yellow, red, infrared, a little bit UV. We know sun emits at UV. We always put sunscreen to protect from that and so on. But it peaks about here. It peaks about the yellowish green. Since it has all the spectrum, they all makes it look yellowish white. This also depends on how hot the sun is. It turns out sun's heat temperature varies. 5,525 Kelvin here. I believe it varies between 5,500 to 5,800 or so. As this varies, the peak emission also might change. So that's just the takeaway extra information to impress someone in your life. Shadows, we won't be really talking a lot about shadows, but it's a general knowledge, right? If we block light with a opaque object, like in this figure here, the opaque object will produce a shadow. If our light is a point source, we'll have just one dark shadow. But if we have a larger light source, there will be some parts that are totally shadowed, no light is passing through, and there will be some parts, some of the light is passing through over here, for example, there. So we will see inside a dark shadow, and out here a lighter shadow. And that's what we also see with these solar eclipse. There are some regions on Earth we see the full eclipse because that's the part where we see the dark shadow, no light is able to pass, and some regions will see partial eclipse. And we will see partially the sun is blocked, but not all of it. The dark shadow part is called umbra, and the faint part is called penumbra. So as we mentioned already, the light reflects in many directions. Some comes to our eyes, and we see what we see. And this is called actually diffuse reflection. There are also some smooth surfaces like a plane mirror, flat mirror, and then light will be reflected in parallel rays. That is called specular reflection. And there is one reflection law we want to know, which is a simple idea. If I'm reflecting light ray from a flat surface, I'm going to look at the angle of incidence, which is the angle between the normal to that surface and the ray, incoming light ray. Again, if I have a light source here sending light ray, there are many rays, but I will represent all those with one ray or two rays if I want to think about it more. And then it will reflect with the same angle. So incoming angle is equal to reflected angle. And we will use that idea in geometry to solve some questions, like in this question here. We have a light bulb here, we have a mirror, and the light rays are already shown. Two light rays are shown here. One comes with an angle, reflects with the same angle from the normal. Here is the normal, perpendicular to my surface. Don't forget, and comes here. This is one, light ray 1. And then they send another one, 2, comes to the other end of the lamp, the mirror, and reflects in this fashion. Well, it would reflect like that. It's too much information maybe, but we don't have anything there. It's the surface, so we look at that surface. The question is asking us, what is this distance? What is the distance from mirror to here, where the first light ray hits? And we will use geometry. And right away I can see that if I look at this triangle here, let me redraw the triangle, but with a different color maybe with a different color. If I look at this green triangle, I am redrawing for you. Right, tangent theta here, tangent theta is equal the opposite 2 meters over adjacent, which is L. So I can use that to calculate L. Switching L and tangent theta, I can say L is equal to 2 meters over tangent theta. And that will give me what L is, which is what we did in here. So all I have to do is know what theta is. I know 2 meters, I'll get L from there. So all of this looks like a pretty confusing image. Once you think about it thoroughly, you say, oh, it's not that bad. It's just how physics works generally. So how do I find that theta? I know this is given me already theta here, right? And if I find it, I find it. They are all inverse and equal to each other. And I can find the theta. That should be this over here. I can use the yellow triangle I'm going to draw here. Oh, yellow, not red, yellow. Let's do that. And this yellow triangle is this here. That, and that overall, right? And I know all the sides there, so I can solve for that easily. I can say then on this triangle, tangent theta is equal to opposite 0.5 over adjacent 1. And from here, theta is equal to tangent to, well, actually I don't have to find theta. I will find tangent theta directly, right? No need to extend it that much. I know tangent theta. Input in there, and I'll get my L. That's the answer. This figure here, let me redo this here, showing if I'm looking from here, the paper blocks this part of the mirror. Will I be able to see the pencil? If there are rays reflecting from the mirror coming to my eye, then I can see their extension. I can see the image, and that's what this image is showing. There's one ray, reflects, comes to my eye. There's another one, reflects, comes to my eye. I look at their extensions. I see the image. Mainly to be able to find images on a flat mirror, we will send 2 rays. For any other mirrors or lenses, we will do the same. And we'll look at if these 2 rays are intersecting. For a flat mirror, we will see that no matter how we send our rays and reflect them, and we'll follow the reflection rule. We'll look at the angle of incidence, right? Angle between the incoming ray and the normal. We'll look at angle of reflection, and they should be equal to each other. And that will give us information that no matter how many I send, the rays themselves will never intersect. Look at this picture here. They're not intersecting, or there, or here. And then we look at their extension, and their extensions will always be intersecting behind the mirror, and that will be the point of image. And if we measure, we will see that the distance of object to the mirror is equal to distance of image to the mirror. Sizes are equal and image is right side up. Since the image is formed here via the extension of the rays, it is a virtual image. Virtual image. Over here, for example, if I have 2.4 meters away an object, the image will be also 2.4 meters away. The distance between the object and image will be 4.8. Alright. So we can easily find the image of an object in a mirror, just will be a cross on the other side. We don't really need to even send rays and see where they intersect. They will be forming on the other side, right side up. This figure is showing that, and it will be virtual image. Generally behind the mirror, right side up images will be virtual. Spherical mirrors behave similarly. We'll send two rays and look at them. If the rays are intersecting, we have real image. If the extensions are intersecting, we have virtual image. Two types of mirrors we have: convergent or concave mirrors, divergent or convex mirrors. And as we send light rays, we will see that mostly in a convergent mirror, the rays will converge to a point and they will give us a real image. Sometimes not though, mainly, mostly. And for the divergent mirror or convex mirror, we'll always see the extensions are convergent on the other side of the mirror, and they will give us an imaginary or virtual image. What we see in these pictures, if we send parallel light rays to an axis we draw through the middle of the lamp, which we will always do, and we will call it optical axis, they will converge to one point, which will be the focal point for a convergent mirror. And if we do the same for a divergent mirror, they will diverge. You see here the rays are all diverging away. There is no way they can intersect after they reflect, but their extensions will be meeting at a point, intersecting at a point, and that will be the focal point of that divergent mirror. We'll be sending special rays. Quickly, I'll review them here and look at where they intersect, and that will be where the images. This picture is showing many rays, but two of these would do. Here are the special rays for convergent mirror. Parallel rays reflects in a way that passes from the focal point. If I send a ray from the focal point, it will reflect parallel. If I send a ray to the middle of the mirror, to the center of the mirror, it will reflect with an angle that is equal to the incoming angle with the axis, optical axis. This is optical axis. Three special rays. Sending two of those and looking where they intersect will tell us where the image is. And we don't even have to send from all points of image here. We send it from the tip of it. We see where they intersect, and we say all the rest will form accordingly. There are billions of rays coming from this, hitting the mirror and reflecting and forming that image. But that two reflections we build will give us the idea. And I will be tempted to use sending a parallel ray if possible for the situation. Ray parallel to optical axis will reflect passing from the focal point, will be that guy here. And rays passing through the focal point, this guy here, will reflect parallel. This guy there, and they intersect at the point of the image. This is a real image upside down and smaller than the object. That's for convergent mirrors. This image here, we have a situation where we have a convergent mirror, and we have focal point at 40 and about 60 centimeters away we have an object. We can overall send two rays to draw this. Parallel reflects from focal point. The one going from focal point reflects parallel, and here is where they intersect. Here is where the image will be. So we find the tip of the arrow we have there, and we complete it down. It will be hidden the optical axis, of course, and image will be this. So image is upside down, larger than the object, and is real because the real rays are converging, not their extension. Here they did the measurements and so on. They calculate magnification, which is the distance of the image divided by distance of the object with a negative sign in the front. We'll get to that later on more. We can calculate how larger the image is using image size over the object size. That's the magnification, and that's directly related to distance of image and distance of object, so this is also possible. We'll get to that later in more details. Divergent mirrors are not as interesting as the convergent mirrors. They always have one type of image, no matter where the object is. Image is here. On the other side, virtual, because always extensions will be meeting at a point smaller than the object, and in between the focal point and the middle of the mirror and the mirror. Special rays still exist. Still will send two rays to see how overall how the image looks, but we will always end up get an image here. It could be there, a little bit closer, depending on where the object is, but always in between the focal point and the mirror. Parallel rays for a divergent mirror reflects in a way that their extension meets at the focal point. The rays that comes with the extension passing through the focal point will reflect parallel. And rays that hits the middle of the mirror will reflect with the same angle of incoming angle with the optical axis. Those are the special rays. We use plane mirror on the left side of our car and a convex mirror on the right side, because left side is closer to us. We can have a wider view and see from close by, but the right side is farther away, so we want to see more viewpoint, and that's what the convex mirror does. It shows the object smaller, but we can see a wider area, which is why we always have this warning here: objects in the mirror are closer than they appear, because that's what the convex mirror does. These are boxes are summarizing what we need to do, what we discussed already. Simply we'll send two rays, we look where they intersect, and that's the point of image. We'll complete the image logically after that. The same for divergent mirrors, only there are differences on how the rays behave, right? And we will also see that always extensions will be convergent while the rays themselves are divergent. That's why it's called divergent mirror. And this page is summarizing for convergent and divergent mirror what type of images see depending on how far the object is. For a concave or convergent mirror, if I'm at infinity and I start walking towards the mirror, if I'm at infinity, my image here at a point not visible, as I come closer and closer, my image goes farther and farther and gets larger. If I reach to a point of 2 times the focal point is shown as capital F here. So if I am at 2F, 2 times the focal point, my image is at the same place as me, inverse real, because rays are intersecting. Remember, we're sending 2 rays and see where they intersect. If I come even closer than 2F, my image will keep going farther away and getting larger. Finally, it goes to infinity if I'm at the focal point and I can't see it anymore. The rays are overall parallel to each other, and we assume they intersect at infinity. There's an image at infinity, we say. If I come even closer than focal point, here's the focal point here, and I am there, I will have a now virtual image. If I send my rays, there's no way they can intersect. And let me delete those. And I will have their extensions intersect, and I'll have a virtual image. So there are many different types of images on concave or convergent mirrors. For divergent mirror, if I'm at infinity, my image is at the focal point. Focal point and invisible, very small. If I walk closer, no matter where I am, my image will be in between the focal point and the mirror, right side up, virtual. Always the extensions will be meeting. It could be larger and smaller, come a bit closer and farther from the mirror, but it will always be in between the focal point and the mirror. And that's the bottom line, the last page of the reflection.